No problem. I have already filled it and I'll show you that table. Can you see this table here? I have already filled it. You know anyway how to do this. I can later do it and check it. So look into this table. So can you conclude that closure property is there? Closure property satisfied? How do you conclude closure is there?
Since all the elements are in the table itself, like from the group.
Table or the elements of the group. Right. Okay. So closure is there. Okay. Associative property. You know very well. Composition of
Composition is associative, then the like it will be satisfied.
satisfied. You know very well. Composition of function is always associative, but it is not commutative. That is different. It is not commutative. Composition F composition G and G composition F are not one and the same, but it is associative. So you can say composition of function is associative. So the elements will satisfy the associative property. Okay, then what is the identity element here? That's very obvious. Here I have used the symbol I. If you want, you can use E. It is up to us. Nama, what is the identity here? How do you identify which is the identity element? Are you all there sleeping?
Yes, ma'am, we are there.
Now then, tell me the identity element here. See, look into the row, right? If you multiply any element with, say for example, I into I is I. Similarly, 1, 2 into what is 1, 2
It
again?
returns
Right?
the number itself.
Yes. So what is the identity element? I is the identity element. Clear? I is the identity element. Okay. Now talk about the inverse. What is the inverse of 1, 2? Inverse of 1, 2 is 1, 2 into what is identity element?
The element itself.
Element itself. So yesterday I told you something, right? All cycles of length 2 are self-inverses. So same way, if you see 1, 3 into 1, 3 is again identity. 2, 3 into 2, 3 is also again identity. That means inverse of 1, 2, 1, 3, 2, 3 are they themselves. Right? So what is the inverse of 1, 2, 3?
132.
132. And inverse of 132 is 1, 2, 3.
2, 3.
So it's very obvious it forms a group. So is it a commutative group? Or the
No.
elements satisfy the commutative property? No. So how do you judge that? First row and first column. Are these values same? First row, if you see, I 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. But here I 1, 2, 1, 3 till 1, 3. Don't look into the first row, first column. It will be the same. Why? Because identity element commute with every element. Always identity element commute with every element. And one more thing, any element with commute with its inverse. Right? So look into the second row. 1, 2, I, 1, 3, 2, 1, 2, 3, 2, 3, 1, 3. Here 1, 2, I, here it is 1, 3, 2, here it is 1, 2, 3, third element. Here it is 1, 2, 3, here 1, 2, 3. Can you see there is a change? So second row elements and second column elements do not match. Similarly, third row elements and third column elements do not match. Right? So these elements, that is the elements of S3 are not commutative. So S3 under composition of functions is not an abelian group. Got it? Hello?
Yes, ma'am. Got it.
Got it. So see, permutation group is a very good example for non-abelian group. Okay, one thing I'll say. So you
Ma'am,
understood.
can you give us an example for four elements like 1, 2, 3, 4?
Wait. That is the thing I'm going to come next. That
Okay.
is some special group, right? I'm going to come. First, let me say about S2. Can you say what will be S2? Any idea? S2, I'll say, then I'll go back to the elements with group with 4 elements. What is S2? One thing I didn't mention, I'm very sorry. This permutation group is called S3 because this is obtained by permuting 3 elements. S has another name, symmetric group. Permutation group is also called as symmetric group. So from that word symmetric group, S has come. So S3, right? So can you guess what should be S2 then? It is obtained by S2 is obtained by permuting. No, I told you 3 elements. If you permute, you will get S3. So how do you get S2? If you permute 1 and 2. So what are all the possible permutations you can have? One is either you can have the same 1, 2, no change, or you can have 2, 1, interchange. 1, 2 means what? Functional notation 1, 2, 1, 2. And what will be the cyclic notation here? Nothing, it is identity. Or even you can write it as I. 2, 1 means what? How do you write the cyclic notation for this?
We can write 1, 2.
1, 2. Only 2 elements are there. So S2 has 2 elements. I 1, 2. Okay. So I'll form the Cayley table now. Tell me, how do you fill this table? Identity into identity is I. Identity is 1, 2 is. Can you fill this table and get me the output? Fill the table and tell me the entries. Please make it fast. I into 1, 2 is what? Identity into 1, 2. How do you multiply? Identity is 1, 2, 1, 2. 1, 2 is
1, 2.
Same 1, 2 you'll get, right? Okay. 1, 2 into I is also same 1, 2. What is 1, 2 into 1, 2?
I.
It's a group. Obviously, closure is there. All elements are what? The elements of all the entries in the Cayley table are the elements of S2 disclosed. So only 2 elements are there. Anyway, composition of function is associative, obvious. So what is the identity here? I. Inverse of identity element I is itself. Inverse of 1, 2 is 1, 2. So it is a group. Clear? This point is clear, everybody?
Yes, ma'am.
Okay. Can you say whether this group is abelian?
Yes.
Of course. See, groups of order. Groups of order 2. Order 2 means what? Groups with only 2 elements are always abelian. So it is abelian here. But groups of order 3 is also abelian. Groups of order 4 is also abelian. 5 is also abelian. But 1 minute. Okay, ma, I'm sorry. So this is an abelian group. So groups of order 2, abelian. Order 3, abelian. Order 3, can you say, give me an example?
One is order 3 abelian because the last thing that we saw wasn't an abelian.
Hey, S3, order 3 group. S3 is an order 3 group. How many elements were there? S3.
Okay, ma'am. Got it.
Six elements. S3 doesn't mean that it has 3 elements. 3 factorial. 6 elements are there. Order 3, can you give one example? You yourself told 4th roots of unity, you told. The same way, if you considered 3rd roots of unity, 1 omega square, it is a group of order 3. Okay, 1. What happened here? Let G is equal to 1 omega square, all 3rd roots of unity. Okay. Omega cube is 1. Okay. And one more property you have, right? 1 plus omega square is 0. Hey, always do remember, whenever you add all the nth roots of unity, it should be 0. It should be 0. 1 plus omega square is 0. So Cayley table forming is very easy here. Under multiplication here. Under multiplication, right? Oh, I'm sorry. Can you fill this Cayley table? Is a group under multiplication. Chalma, yes, can you please fill this table very fast? Omega cube is 1. That you have to remember. 1 into 1, 1. 1 into omega square. Only multiplication, mere multiplication. Usual multiplication. Omega square. Omega into omega square. Omega cube, that is 1. Omega square, 1. What is omega power 4? Yeah. How do you calculate omega power 4? Omega square into omega square is omega power 4. It is omega cube into 1. 1 into omega. So the way I have filled the table, is it clear?
Yes.
Hello? Yes, Pa. So can you say that closure property is satisfied here?
Yes.
Yes. Okay, identity. What is the identity here? 1 is the identity. It's usual multiplication, right? See, for under usual addition, 0 is the identity. For usual multiplication, 1 is the identity, right? So 1 is the identity. Okay, closure and write. All elements in the table are the elements of G, hence G is closed under multiplication. Number 2, associative property. Multiplication is always associative. So I told you 2 properties depends upon the operation. What are those 2 properties which depend upon the operation?
Associative and commutative.
Associative and
Commutative.
commutative. Very good. Very good. So identity 1 is the identity. 1 is the identity, and it is obvious from the first row and first column. Correct? Why do I say first row and first column? Can you please look into that? Why I say like that? Yeah.
1 into 1
1 into 1 is 1. 1 into omega is omega. 1 into omega square is omega square. So same way, if I look into the first column, 1 into 1 is 1. Okay. 1 into 1 is omega. Omega square into 1 is omega square. So both the ways it is satisfied. So it is 1 is the identity. Inverse, ma? Inverse of 1 is 1. Always you remember, identity element has inverse of identity is its own. Okay, inverse of omega.
Omega square.
Omega square.
Very good, omega square. So inverse of omega square is omega.
Omega.
So hence G is a group. Okay, is it commutative? Abelian property, can I say it is an abelian group? Commutative is a property.
Yes,
So
it
when
is.
it satisfies commutative property, the group becomes abelian group, right? Okay. Can you say whether G is an abelian group?
Yes, commutative property is satisfied.
Because multiplication is always commutative, right? Okay. So G is abelian. Abelian group because usual multiplication is commutative. Usual multiplication is commutative. Okay, ma. Somebody asked for groups of order 4, right? Okay, now I'm going. See, very important. Some special group I'm going to show you.
Ma'am?
Science 4
Ma'am?
group. Yes, ma. Tell me.
Ma'am, can you please show the previous slide? Just for one
Yeah.
second. Okay, ma'am, we can move.
Yeah.
Next year.
Science 4 group. It is named under the mathematician Felix Klein. Actually, he has given this group description. He has found out one group with all these properties. Actually, this group has 4 elements here. P is the identity element. Okay. So what is the speciality of this group is, if you square each and every element, you will get identity. See, of course, identity also, if you square, it's a group under multiplication, yeah, very important. Square means not simply squaring. I'm wrong in some way. I should not use this. 1 minute. I'll define this in a different way. Okay. Let G, comma star be a group where G is equal to EABC, such that E star E is E, A star A is E, B star, the star can be any operation here. So I'm not fixing a specific type. It is only a group description. See, you can find such groups in many things. I'll show you 2 or 3 descriptions like this. This is just a generalized version. There exist 4 elements. It forms a group in such a way that all these properties are satisfied, right? C star C is E. These 4 properties are one more property. A star B and B star A are one and the same. It is C. A star C and C star A are one and the same. It is B. B star C and C star B is one and the same. That is A. So if you operate 2 elements, you get back the 3rd element. Just leave a set asset identity element, because you know very well if you multiply any element with identity, you get back the same element. So have you understood the group description now? So if you are in the process of filling the Cayley table, how will you fill this? Use this description and fill it. Can you fill it? Take 1 minute time. Use this description. I have given you certain description. Use that and fill this. So closure property you need not check, because already the way you have defined, you covered everything. It is already closed. Nama, can you fill the table, please? First row. In the middle, all are taking rest.
Ma'am, what would be E star A, ma'am?
Mama, star I'll put here. Here also, Engama should be E star A. E star E. Yes, E star E is E. See, E star any element. E star A is always A and that is also equal to A star E. Because E is supposed to be the identity element, right? This will be satisfied for everything. Even you can go for B, C, everything. Now can you fill the first row? E star E is E. Here what you have tried. E star A is A. E star B is B. E star C is C. First column A star E is A. B star B is C. It's not allowing me to write. Okay. So can you say what is this element? A star A, va? I'm keeping a dot here. What is A star A?
E, ma'am.
E, ma'am.
A star B here next.
C, ma'am.
A star B, ma?
C.
C, C. Next.
B, ma'am.
B.
Okay, then set. I'm going to the third row now. B star A.
C. C.
C. B
E.
star E. Good.
A.
A. C star A.
B, A, and E, ma'am.
A and E.
E.
So it's very obvious. Closure property obvious. Closure is obvious. Okay. Associative is also obvious, right? It's obvious. You can check. Associative is also obvious. See, whenever some group is commutative, automatically it will be associative. But if it is associative, it need not be commutative. You can think about this. See, whenever an operation is commutative, it will always be associative. But whenever an operation is associative, it need not be commutative. See, you know, composition of function is associative, but it is not commutative. Right? Okay. Associative is also obvious. E is the identity element. Inverse of every element is itself, right? Inverse of every element is itself. This is actually only a group description here. Why I say only a group description here? Because there is no specific operation mentioned here. I'm just going for a generalized thing star I'm saying. So even if you replace by star, so you can find some 4 elements. If you replace star by some particular operation, if these properties are satisfied, that can also be called as a client's 4 group. Got it? Hello, bache?
Yes, ma'am. Yes, ma'am.
Yes,
Okay.
ma'am.
Okay. So now somebody asked for groups of order 4. So groups of order 4 is abelian actually. I should say that, right? 1 minute. Why I didn't complete the statement. Okay. So also, okay, A star B equal to B star A for all A comma B in G. So G is an abelian group. Very important. Groups of order 4 is abelian. Okay, so now I'll go for a particular example where you can see this client's 4 group. Right? What I do is I take G is equal to 1357. 1357. 4 elements I take. Okay, I'll write prove. G is a group under multiplication modulo 8. Multiplication modulo 8. Very important. What do you mean by multiplication modulo 8? A is an element, B is an element. Solution. A is
Dividing it by 8.
A multiplication modulo 8, B means what? It is the remainder obtained by dividing AB by 8. Correct? Dividing AB by 8. Concept clear? Concept clear?
Yes, yes, ma'am.
Yes, ma'am.
So I'll show that this is not only a group, it is exactly Klein's 4 group. To satisfy all the properties of Klein's 4 group. One description is given already, right? All those properties that is being mentioned there, that will be satisfied here also. I'll do one thing. See, 1, 3, 5, 7, 1, 3, 5, 7. Operation is multiplication modulo 8. Please fill this table. Make it fast. Okay, I myself will fill because it may take time. Then you may not. 1, 3, 5, 7. I think you know how to fill this, right? See, for example, 3 multiplication 8, 3 na. 3 into 3 is 9. 9 when divided by 8, the remainder is 1. Okay. What is 3 multiplication modulo 8? 5.
7, ma'am.
7. 3 multiplication modulo 7. Modulo 8, 7. What is it? 5.
5.
5. Will this operation be commutative? Multiplication modulo 8, will that be commutative? Of course, right?
Yes, yes, ma'am.
Because why I can say
Multiplication operation is there.
multiplication. After all, you are going to multiply 2 elements. Any order you multiply, A multiplication modulo 8, B means multiply A and B and divide by 8. So B multiplication modulo 8 A means multiply B and A and divide by 8 to get the remainder. Both ways you will get the same remainder. Okay. So 3, 1, 7, 5. And here 1, 3, 1. So what are the properties that you can observe here? One is the identity.
Closure
Right?
is satisfied.
Closure. First I'll write with closure. Good. I'll write closure is obvious, but don't write that the same sentence in your exam. You have to write from the table, all those things. At least there is a formality, right? Everything cannot be. So closure is obvious. Okay. This is
Associative is also.
that you can write. Multiplication modulo 8 is associative. That you can write. It is after all multiplication. Okay. So what is the meaning? What is the meaning of this? And what way it is differing from this? No difference. Right? No difference. That's not going to differ. The only thing is you will take the remainder and multiply, but it won't differ. It will be the same. Associative. One is the identity. What is the inverse of every element? Inverse of every element is
itself, ma'am.
itself. The same Klein's 4 group here, right? Inverse of every element is itself. Is itself. And that is a square. That is 1 square, 3 square, 5 square, 7 square. All are 1. Here I can write square, yeah, because 1 into 1 multiplication only, right? Okay, I won't write square. Better I'll use the correct notation. What notation I have to use actually? How should I write this?
X8.
That is better.
Ma'am,
Yenama, yes, tell me.
can you explain associative property?
Yes,
Whatever.
I have doubt around it.
Associative property, yeah, 1 minute.
With an example like with 3, 5, 7, something like that.
Yes, we'll do. What is 5 into 7? 35. 35 when you divide by 8, and if you get the remainder, 3.
3, ma'am.
Again, this will give you 1. So same way, 3 multiplication modulo 8, 5. What is this value?
7.
7. 7 into 7. 1. Any way you multiply, this is not going to change. You can take it for granted. Multiplication modulo 8 is always associated. Clear? Even addition modulo 8 is also associative. You can take it for granted. Nothing will happen. You can write it is always associative. So,
Ma'am, just one doubt. If just one property one element satisfies from the table, then does it mean the whole thing is associative? Whole thing proves for associative property.
Here because of the operation. Here
Okay.
the property holds good because of the operation. Multiplication modulo 8, that operation is associative.
So if there is a different operation, then should we test for all the elements?
Yes, yes.
Okay.
Don't worry, that type will not come. For infinite group, you will do infinite group also 1 and B. Wait 1 minute. So this is clear? Okay. So also 3 multiplication modulo 8, 5 is equal to 5 multiplication modulo 8, 3 is equal to 7, the third element. Similarly, 5 multiplication modulo 8, 7 is equal to 7 multiplication modulo 8, 5 is equal to 3. Then, which 3, 7 I have to take. So, from the above, it is obvious that G, this is a Kleins formula. I'll give you one homework now, right? Prove that. Okay. G is equal to 1001, minus 1001, 100 minus 1, minus 10, 0 minus 1. It is a Kleins formula under matrix multiplication. See, usually, so Kleins for group means this is what? Abelian group. But usually you know very well, matrix multiplication is not what? For any two matrices, can you say always? It's not commutative. But particularly if you choose only these 4 matrices, it will be commutative also. Okay, you can prove that this is a Kleins formula. So for that, what you can do is you can name them A, B, C, D. You can form a Cayley table, do all the necessary things, check and tell me tomorrow. If possible, you try to find another Kleins formula also. Right? Okay, va. Okay, I'll proceed with the next.
Ma'am?
Yeah, ma'am. Yes.
For a group to be to satisfy Kleins for group, they have to be abelian group. No? They have to satisfy.
Not only abelian. The same way it is described. There is some what a modeling type is there, right? All the elements are self-inverse. If you multiply, leaving identity, if you operate binary operation between any two elements, you have to get back the third element. All those things should be there in this.
So you have to prove all those 4 properties along with
Yes, the way I have written here, right? See, multiplying 2 things, you get the third element.
So of these 5 properties, if anyone fails, then
it is not a Kleins formula. Okay.
Ma'am, one doubt. So when we are doing the Cayley table for this, instead of writing numbers, we have
you can use ABCD.
Oh, okay.
You can use ABCD, but separately you can evaluate. Okay, you can do the calculations below the table or above the table. It's up to us. Okay. I gave you already. See this one, right? Even you can take down this question here. G is equal to 2468. 2468. It is a group under multiplication modulo 8. It is a what is identity element here? Hey, what is the identity element here? Can you see
6,
the
ma'am.
6 is the identity element? Can you see some difference in this particular question? Can you try this question? Prove that G is equal to 2468 is a group under multiplication modulo 10. Okay, take down, you can try later. I'm sorry. Okay. Now there is a very important concept called finding an order of a group, order of an element. Just 5 minutes, I'll take order of an element. Order of an element. Order of an element means, suppose A star A is E means by operating A twice you have taken A, right? That gives you E. Then order of A is 2. Suppose A star A equal to E. Only after operating minimum 4 times if you operate, if you are getting E, then order of A is 4. See, this should not happen. Right? See, only after operating 4 times if you are getting the identity element, then order of A is 4. Okay. See, for example, okay, proper notes is there, don't worry. For example, I'll take Z4 under addition modulo 4. So Z4 has 0, 1, 2, 3. So what is the identity element here? What is the identity element here? Enema, what is the identity element here for Z4 under addition modulo?
0, ma'am.
0, 0. Set, okay. I'll find the order of each and every element. Okay. What is the order of 4? 1. 1 I'm adding with 1. Are you getting 0? 2 times if you add, it is 2. 3 times I'm adding. It is 3, not getting 0. 4 times if I'm adding. What is this now? 4 times if you add, I'll get 4.
0.
0. So order of 1 is 4. Then order of 2. If I add 2 times, what I get?
0.
0. Order of 2 is 2. Order of 3. 3 if you add 2 times, what you get? Order of
2.
modulo 4. Huh?
2, ma'am.
2. Okay, ma'am. Then 3 addition modulo 4, 3 addition modulo 4, 3.
1.
1. So 3, don't worry, this is solved somewhere later also, that you can see. 4 times if I add,
0.
0. So order of 3 is 4. Order of 3 is 4. So have you observed something in this order of an element? It is something related with the order of the group. Order of an element and order of the group, somewhere they are related. If you look into 2, okay, what is order of 2? It is 2. Why? Because 2 into 2 is 4. If you look into 3, what is the GCD of 3 and 4? It is 1. So order of 3 is the complete 4 will come. Only if you add 4 times, you will get 0. Okay, this is not necessary. Leave it. I need not confuse you. Just an observation. That's it. Okay, so tomorrow I'll start with subgroup. Okay, subgroup. So these are all the elementary properties of group. Just to look into this. Don't worry about this. If you have a group G comma star, then always the identity element of the group is unique. There will be only one identity element. And if you take any element X, that particular X will have only unique inverse. I cannot say inverse of an element A is both B and C. Not possible. Inverse of A is there is only one element. If at all, if it exists, it can be only one element. Right? Okay. Cancellation law, just look into this. See, whenever you have such thing, A star C equal to B star C now, then I can cancel out these two things and I can say that A and B are same. This is called cancellation law. Similarly, I can do it in the other way. If C star A equal to C star B, can cancel this way and I can say that A and B are equal. These two are called cancellation law. Just don't worry about these. Proof and all not needed. I'll tell what is a subgroup and then close. I'm not going to do any problems now. Suppose G is a group under operation star. H is a subset of that. We note the point, H is a subset of that. That is, elements of H are also the elements of G, but not necessary that all the elements of G are taken inside H. Right? So H is a subset. So if I want to say that H comma star is a subgroup, then H comma star should be a group itself. H comma star should be a group itself. So G comma star is a group. H is a subset. So for that subset to be a subgroup, that subset should be a group under the same operation. Then we can call that subset as a subgroup. Okay. Better I'll stop here.